Our next presenter is Noah Folty, and the title of his presentation is Multi-Mode Quantum State Tomography of Slow Light.
Thanks for the introduction, and thanks to my research advisor, Dr. Andrew Dawes of the Physics Department. I'd also like to say thank you to my research collaborator, Hunter Dassenville, who just presented. Many of you were here. So my research project is actually related to his. It's the topic of my presentation is the detection of quantum states of light from a stored light process. Before I dive in here, let me give you a little background and motivation for my project. Electronics are used universally in today's communication and data networks. As people make more and more use of communication networks, the data infrastructure is always having to expand and speed up to accommodate the increased bandwidth. However, there's a problem since electronics are approaching some speed limitations that can't be easily overcome. So, for example, copper wires have a maximum transfer or data rate of around 20 gigabits per second, and CPUs have been stuck at around 3 gigahertz for a number of years now. Electronics are just at the point where they can't be improved all that much. One possible solution to the bandwidth issues in communication networks is to use photonics, or optical computers. Photonics can have potentially a much higher bandwidth than electronics. Fiber optic links currently in use between data centers have data transfer speeds in excess of 40 gigabits per second, which is already a lot faster than electronics. Photonics are also still in active development, so there's a lot of room for future improvement. So, what makes electronics and photonics fundamentally different? If we look at an electronic computer, data is carried with electrons over wires. This data is then processed by switches or transistors and stored in memory or RAM for quick access. While a photonic system is based on different principles, it does have analogous system components. So, as the name implies, photonics carries data with photons, which travel through fiber optic cables. The data is then processed by optical switches and stored in optical memory. You'll notice that there are question marks by the optical switches and the optical memory. This isn't because we don't know how we might make these components, but rather there are a number of competing technologies right now, and we don't know which will win in the end. My project focuses specifically on optical memory. For my research, I'm using an optical storage method which is known to allow for the controlled storage of light. The optical memory cell uses a nonlinear optical process known as electromagnetically induced transparency, or EIT for short. In a nutshell, EIT allows one beam of light to control how another beam of light propagates through an optical medium, in our case, rubidium. For our optical memory cell, this means that we can control how long we store a signal pulse of light with another controlling beam of light. Other researchers have already used this method to store light before, so we know it works. But as of yet, the retrieved light has not been fully characterized. So we know we can send a pulse of light in, and we can retrieve that pulse of light back at an arbitrary time later, but we don't know exactly what it looks like when it comes out. There are a number of things that we must consider when we're characterizing the output of our optical memory cell. First, there's the pulse shape, or the amplitude of the light versus time. There's also the light polarization, or the orientation of the electric field of the light, and the wavelength or frequency of the light. Finally, there is the spatial mode of the light. Other researchers have already characterized the pulse shape, and we know from the optical process that we're using that the polarization and wavelength of the light are unaffected. However, the spatial mode of light from optical cells, storage cells such as ours, have not been characterized yet. This is specifically where my research is focused. So, what is a mode? That's a good question. Simply put, a spatial mode is an elementary solution to the electromagnetic wave equation, which governs how light propagates. A good example of a mode is the plane wave, as shown in the illustration. Any possible light wavefront can be described as an overlaying or a superposition of some number of modes. Let me describe for you a plane wave mode. Imagine there is a point source of light way over on the other side of the room, and it's radiating coherent light equally in all directions. If we follow a few of the photons from that point source of light to the region in front of me, there are a few characteristics we'll notice about this light. First, the photons are traveling nearly parallel to each other. If we take a cross-section of our light perpendicular to its direction of motion, there are a couple other things we'll notice. First, all the light in this cross-section is in phase with itself. In other words, all the photons are at the same point in their oscillation cycle. Additionally, we'll notice that the light amplitude is uniform throughout our cross-section. In other words, the same number of photons hitting every square centimeter of our cross-section. These properties describe a plane wave mode. Another way of thinking about light is in terms of wavefronts. The light on this slide is exactly the same as in the previous slide, it's just that the red lines now represent wavefronts. Wavefronts are simply regions where the electric field of the light is at a maximum. Now let's add or superimpose another plane wave on top of this one at a slight angle theta to our original one. This is called superposition, as I mentioned before. This second plane wave that we just added is a new mode of light, since it's at a different angle to the original one. So different angles of plane waves correspond to different modes of light. If we look at the cross-section where these two plane waves are meeting, then we'll notice that at some regions they add to each other and some they subtract from each other. This results in constructive and destructive interference and makes for bright and dark regions in our cross-section, or what we call interference fringes. Let's back up a little here and take away that angled plane wave. So we're only left with our original unangled plane wave mode. I'm going to be referring to this particular plane wave mode as the reference beam, or the reference mode from now on. On the right, I've added an intensity graph of our cross-section. So the horizontal axis is simply the position on our cross-section, and the vertical axis is the intensity of the light at that point in the cross-section. Now, if we add in our plane wave mode again, or another angled plane wave mode, then we see that the intensity in our cross-section varies sinusoidally. Now, this plane wave that we just added in at an angle is what I'm going to be referring to as a signal beam. The signal beam can be anything we want, really. It just, in this case, it refers to the superposition of all modes besides our reference beam. So all modes besides our reference beam comprise our signal beam. If I change my signal beam so it has a different mode of light, we see that, or in other words, a different angle of light, we see that our intensity graph changes. It's still sinusoidal, like it was before, but this time the peaks are closer together. So different angles of plane waves make different frequencies of sinusoids when they interfere with the reference beam. If we have both of those angled plane waves in our signal beam, we now have two modes present in our signal beam. And when that interferes with our reference beam, we get an intensity graph that looks something like this. When you look at this, you can still tell you can tell what modes are contained in our signal beam just by visually looking at the intensity graph. But you can imagine that if we had a whole bunch of different modes in our signal beam, it would be difficult to tell exactly which modes are present. So if we have some arbitrary signal beam, we might have an intensity graph that looks like that. Just by visually looking at that, there's no way you can tell what modes are contained in your signal beam. We need a more systematic, a better way to determine which modes are present in our signal beam. So enter the Fourier transform. The Fourier transform is a mathematical transformation that relates a spatial domain to a frequency domain. In our case, we're relating the cross-section intensity graph to a mode or frequency graph. In general, the Fourier transform takes an arbitrary function and finds the unique sum of sines and cosines that add up to make that original arbitrary function. So if we start with a square wave function, we can express that square wave as the sum of multiple sinusoids of different frequencies, as shown here. The blue sinusoids are what comprise that square wave. What the Fourier transform does is it finds what those frequencies of sinusoids are and what their relative strengths are. So on the blue graph that's about to show up, the horizontal axis is the frequency of the sinusoid, the vertical axis is the strength of that individual frequency of sinusoid. So that's the Fourier transform graph for a square wave. Let's apply this to what we were just looking at with modes. Now we're back to just the reference beam and the intensity graph. If we apply the Fourier transform to our intensity graph, we'll get a Fourier transform graph or an FFT graph that looks something like this. The central spike corresponds to our reference beam. You'll notice that it's at the zero position on our horizontal axis. That's because that's our reference, so it's 0. If we add in a signal beam with one mode of light, we'll see that two side peaks appear on our FFT graph. These two side peaks actually refer to just one mode of light. It's just that the way the Fourier transform works, it ends up mirroring across the 0 axis. If we change our signal beam so that we have a different mode, then we still have those two side peaks on our FFT graph, but this time they're farther out. So the Fourier transform is able to distinguish that from the previous mode of light in our signal beam. If we have both modes present in our signal beam, we have two pairs of side peaks on our FFT graph. So we still have the central peak for the reference beam and two sets of side peaks for the two modes present in our signal beam. If we have some arbitrary signal beam with some unknown number of modes, we can apply the Fourier transform to our intensity graph that results from the interference with the reference beam, and we can determine exactly which modes are present in our signal beam just based on that. And that's really powerful. Now to our setup. In our setup, we have a reference beam, which we know to be a simple plane wave, and it's directed onto a CCD camera. We also direct the signal beam from our optical memory cell onto the CCD at a known angle to our reference beam. This will produce an interference pattern on the CCD, and by performing Fourier analysis on the interference pattern, we'll be able to determine exactly which modes are present in our signal beam. One challenge that we're going to have is that our signal beam is actually much weaker than our reference beam. So visually, the interference pattern is going to be indistinguishable to the naked eye. But using Fourier analysis and statistical analysis, we shouldn't have any problem with this. So far, we've been testing our equipment and our coding using a dummy signal beam, which contains only one mode of light, so it's a simple plane wave. And it's at a known angle to our reference beam. We also have a filter that we place in front of our signal beam, so that's to reduce the intensity of the signal beam, like we would expect to get an intensity that's about what we would expect from our optical memory cell, since it's going to be a really weak signal. And so when we take data with this setup, we expect to get an FFT graph that looks something like this. So we have the central spike corresponding to our reference beam, and then the two side peaks corresponding to our signal beam. We've actually taken data using this setup. I should reiterate, this graph, the horizontal axis is the frequency, or the mode that we're looking at, and the vertical axis is the amplitude of that particular mode. So anyway, we've taken data with this test setup, and we get pretty much exactly what we expect. So we have the central spike for the reference beam, and the two side peaks corresponding to our single mode reference, single mode signal beam. So this is confirmation that our method is working. This graph is actually a little deceptive though, because the Fourier transform actually gives us a complex number, a number with real and imaginary components for each mode. So if we choose one position on our horizontal axis here, say 450, corresponding to that peak right there, it looks like it has a strength of 13 on our arbitrary scale. But this value is actually the absolute value of a complex number. So if we take many different data samples and look at just one particular mode, say this one, our side peak here, if we look at that 450 mode and place those many different data points on a histogram, we get something really interesting. This is what's known as a phasor or a phase vector diagram. The horizontal axis is the real axis, the vertical axis is the imaginary axis. Notice that the origin of the graph is at the base of the white arrow. The way to interpret this graph is that the measured strength of the mode is basically the distance that a point is from the origin of the graph. And the angle that point is from the horizontal axis of the graph is the phase angle of the mode. This graph is actually a combination of 4 different data sets. So we used 4 different filter values in front of our signal beam. So with the grouping that's marked 4.0 ND, we had a really strong filter in front of our signal beam. So we expect to get rather weak modes. And indeed, it's really close to the origin. It's closest of all the groupings to the origin, like we would expect for a really strong filter. As we decrease the filter values to 3.0, 2.0, and 1, you'll see that those groupings get farther and farther away from the origin. So this is further confirmation that our method is working as expected. Additionally, you'll notice that not only do these groupings get farther and farther from the origin, they also tend to spiral out. This is because the different filters that we use in front of our signal beam are actually of different thicknesses. So that variation in thickness is enough to cause a phase shift in the light, which is causing our mode phase to rotate. This is yet further confirmation that our method is working as we expect. So our mode detection method seems to be working pretty well. And now all we have to do is to finish calibrating our stored light setup and then begin taking real data. Any questions?
So if you go back to the previous slide now, that one, yeah. So if you could take it at 1.5 ND, would you expect it to lie on that spiral type of thing?
I think so. I believe so. We haven't actually tried that, but based on the behavior that we're seeing here, that's what we would anticipate. Yes?
I have a related question. So you said the phase angle is determined by the thickness of the glass of the right, which makes sense.
Yes.
But so you could measure the thickness of your 2 filters, right? And
Yes.
you know the change in thickness. And so presumably you can calculate what the phase angle difference is you expect when you go from the 1 to 2 filter or whatever. Have you done that?
No, we haven't
To
yet.
see if it matches up with what you measured.
Yeah, we haven't yet actually. That is a good idea though.
How do you actually measure? So you have the real and imaginary part. How's that actually measured in your experiment?
Well, the Fourier transform is able to basically distinguish the phase of the sinusoid that it's outputting. So the Fourier transform returns a complex number, and if it were just real, that would mean that all the modes were in phase with each other, but the different modes will have a different relative phase to the reference beam. And so you end up getting numbers that are in the complex plane rather than just on the real axis.
And then what would your, so you said future work is to measure your actual signal. So what would that look like? Say, I mean, presumably you're saying you plot it on a picture like this.
Yeah, that's a good question, and I guess that's what we don't know really, actually. So we've developed a method to actually detect what the modes are in such a setup, in a stored light setup, but we haven't done that yet. So that's our next step, really.
Well, I mean, let's say this. I mean, so in the stored light up setup, you know what pulse you're putting in.
Yes.
Right? So is that a plane wave? Is that a combination of plane waves?
Yeah. What we're going to do is we're going to, first we're going to measure the input pulse using our setup to determine exactly what modes are going into our setup. And then after that, we will actually send that input pulse through our optical storage setup and measure how those differ from our original pulse that was going in. Any more questions?
Okay, thank you.